Good morning, everyone. My name is Andrew Callender. I am an undergraduate researcher at Louisiana State University in the Department of Civil and Environmental Engineering. My research topic is about using Louisiana's local resources to create low-carbon concrete. To conduct this project, I had the help of my PI, Dr. Yinfeng Su, and a PhD student, Halula Taj. So I think it's important to start with what's the importance of low-carbon concrete. Currently, the cement industry is responsible for around 8% of carbon emissions. That's a huge number, and majority of that, or about half of that's coming in the form of the embodied carbon found in the limestone that we use to create clinker. So there's really no way to go about creating lower carbon concrete unless we find some way to substitute this clinker or alter it. The ACI recognizes this as a huge problem, as seen in the creation of ACI Code 323, and there's been many promising technologies to reduce this carbon emissions, like using silica fume, fly ash, and slag. But the specific topic that I want to focus on today is limestone calcined clay, or LC3. LC3 is shown to reduce carbon dioxide emissions by approximately 40%. It works off a new type of mix design that you can see in that photo to the right that replaces some of the clinker that's usually used in an OPC mix with both calcined clay and limestone. So first, for the clay that's used, you can't just really get any clay from the ground. It must have the specific mineral called kaolinite present in it. This is the most reactive material that's found in the clay, and that's what's most important. It's typically most economical if you can use a clay that has a low-grade kaolinite content in it. And if it has something, let's say, in the 90 to 100 percentile range, then there's going to be too high of a demand for it in other industries, such as like the pottery and porcelain industry. These clays are typically characterized as Alfisols and Ultisols. And as mentioned previously, this is a Louisiana-based project, so you can see that Louisiana is truly covered with these clays of Ultisols and Alfisols. For this research, we took 6 clay samples from across the state. Each of the areas that we sampled from are shown with those purple stars on the map. For the second main supplementary cementitious material used in LC3, it's limestone. You can think of limestone on a chemical level as calcium carbonate, or CaCO3. And we saw a potential to make an even more environmentally friendly mix by replacing this limestone with powdered oyster shell. Just on a chemical level, the oyster shell is also calcium carbonate. However, it does have a bit more of impurities found in it. And there's currently a huge environmental impact through our waste in the fisheries industry. 10 million tons of mollusks are wasted per year, and there's, in Louisiana, about 475 million oysters produced, with largely of those going to waste as well. These waste deposits can be truly harmful to marine environments, as seen in that picture in the top right, where there's an algal bloom happening from too much waste being placed there. And then secondly, there's a carbon saving through using the oyster shell instead. To get the limestone, you have to quarry it, and that's a mining process that does involve more carbon emissions, but if it's just a recycled material, it's going to inevitably involve less carbon emissions. For the clinker that we used in this project, we wanted to get raw clinker that wasn't already intermixed with gypsum so we could control the mix design better. Our clinker was delivered grinded, but it wasn't truly fine. You can see that in the picture to the right, where there's still a good bit of pebbles and larger particle sizes found in it. So we had to grind the clinker ourselves within our lab. We tried multiple different testing times, and in general, the longer that was grinded was better. But we ended up deciding on a 30-minute grind time for the point of efficiency. It was able to get a one-day strength of around 930 psi. And secondly, we didn't have to deal with the heat that you would deal with when dealing for long grinding times, and also just the timing efficiency. Now, I know I've been talking a good bit about the kaolinite present in the clay, and the way that we determined it is through using TGA, or thermogravimetric analysis. We tried these on all 6 of the clay samples, and the process involves analyzing the weight loss that occurs from 400 to 650 degrees Celsius. During this process, there's an effect called dehydroxylation that happens, where it leaves water molecules coming off of the kaolinite sample. We use the equation that you can see in the bottom right that shows that mass distribution and how you can transfer the weight loss into kaolinite present. We found a range of 4 to 20% kaolinite, which is rather low for LC3 clays, so naturally we chose the highest number, which was that 20% kaolinite present. Furthermore, for material characterization, we did a particle size distribution using a laser diffraction method, and then also XRF to determine the oxides present. For the particle size distribution, we found that the limestone and oyster shell had relatively similar sizes, which does bode well for good substitution. And then one thing that was truly interesting was that the clay was seen to be much finer, which could optimize packing in blends that use the clay. For the XRF that we conducted, we again found a lot of similarities between the oyster shell and the limestone. As you can see to the right, for calcium oxide and limestone, it was 93% around, and then for the oyster shell, it's 86%. The oyster shell had a bit more of impurities, but of course, that's to be expected. One thing that was slightly disappointing from our XRF analysis was we found that the clinker had a bit lower of lime present than you would typically want from a clinker, only about 54% when you really want to see a 60 to 65% range. So we used 3 different binders to test in this experiment. One was just an ordinary Portland cement binder that just used clinker and gypsum. A second one was LC3, using that same mixed design that I discussed earlier on the first few slides. And then a third one that replaced all of the limestone used in LC3 with completely oyster shell. We had a ratio with our mortar mixes of a 1 binder to 1.5 sand and water to binder ratio of 0.4. With these 3 binders, we conducted compressive strength tests on them. You can see there's a very noticeable difference at the 1-day strength that the blend with ordinary Portland cement is much stronger. This is to be expected as LC3 and the OC3 rely off of a pozzolanic reaction, which does take longer to occur. That's why even on the 3-day, the OPC is still much stronger, but it's actually whenever you get to the 7-day that you can see that the LC3 and the OC3 are catching up in strength much more. And because of that rapid growth happening between 3 and 7 days, we believe it's reasonable to expect that at 14 and 28 days, you could see the clay blends actually being stronger than these clinker blends. Now, this isn't to say that LC3 and OC3 will always be stronger than the cement present. Again, as I mentioned, there was lower lime content, and the particle size distribution for our clinker wasn't perfect, so those are things to keep in mind when looking at these results. In conclusion, just kind of a summary of the work that we conducted. We selected clays from across Louisiana. We performed TGA, particle size distribution, X-ray fluorescence tests, and compressive strength tests. We found a large difference in the 1-day compression strengths between the OPC and the clay blends. However, as time progressed, we noticed that that gap narrowed. For further work we would like to do, as I mentioned earlier, 20% isn't a high amount, so we would like to source more clays to get a higher percent of kaolinite. We would like to conduct more activation tests looking on a microscopic level to see how the limestone versus how the oyster shell reacted to see what was truly happening chemically. And we want to monitor the strength development of our other mortars that we have in lab for going for 14, 28, 90 days. We were only able to present up to 7 days because of time constraints. Another important test that we would like to do is durability. LC3 is typically shown to have a superior durability according to the literature, so we were trying to see if that trend will hold true with OC3 as well. And then another idea is doing partial substitution. So in this experiment, we did a complete substitution with oyster shell, but you could do a partial one where only 50% of the limestone is substituted. I would like to thank the funding agencies that helped with this work, the NSF and LSU, and then also ACI for allowing me to speak today. I appreciate your attention, and if you have any questions, I'm willing to answer them.